taken some of these notes, I think, right? Where exactly did we stop? So we got their notes out, so you can tell me exactly where they stopped. I'm going to continue on from there. Just drew the picture? You just did Millikan's experiment? Okay. Hovering stuff. Okay, so we're ready to start Rutherford's experiment. Okay. So Rutherford, okay, another English physicist. Actually, not just a physicist, he was a student of Thomson. So when Thomson was doing his experiments to figure out that there were electrons, Rutherford was probably setting up those experiments. Okay? Rutherford was probably doing those experiments, making the tubes, right? Because somebody had to make all those tubes with different metals inside of them. Somebody had to get the vacuum out and then put in a little bit of gas in. Okay. Now I put English. If you talk to the rest of the world, they'll say he's a New Zealander, but he was born there, but he did all his work in England. Okay, notice the time frame, it's 1910. So this is just about when Thomson's idea of the electron is being accepted. Okay, at 1897 is when they said he came up with it, but it wasn't widely accepted until about 1910, until the old professors died. Okay. And since he helped set up the experiments, he thought that plum pudding model was right. It had explained everything he had seen. Atoms still had whole pieces, but you had these little negative pieces that could come out. Everything they'd seen about an atom, the plum pudding model described. So Millikan was trying to figure out the charge and mass of the electron. Okay? So Rutherford wanted to do something different. He wanted to actually see how big the atom was, because they didn't know how big atoms were. They knew there were little tiny particles they couldn't see, but how tiny are they? So that was his goal. It was about size. I want to learn more about the atom, so he was looking for how big is the atom. Okay? And to do it, he used radioactivity. Radioactivity had just been discovered in the late 1890s as well. So he's got a whole bunch of he's got some new stuff. And nobody knew why radioactivity worked, but they knew that one kind of radioactivity is alpha particles. We'll learn later that an alpha particle is a helium nucleus. But for right now, the important part is that the pieces are positively charged and they're much heavier than electrons. They're pretty big, massive pieces. So they were 30,000 times heavier than electrons. That's what I meant by heavier than electrons, 30,000 times. No, I got that wrong. Only 10,000 times. Only 10,000 times heavier. But that's plenty, right? Okay. So what this gave him was a positive particle he could shoot at stuff. Okay. And what he wanted to shoot at was atoms. But he didn't want to shoot at a whole bunch of atoms. He wanted to interact with as few atoms as he could. So he chose gold foil because gold foil can be made just a few atoms thick. It's the most malleable of metals. Oh, much, much thinner. In fact, it's gold leaf. Anybody ever use gold leaf? Okay, to move gold leaf around, do you use your finger? Not very much because it tends to smear. What you want to use is a brush and pick it up with a brush and then just wipe it on with the brush and it'll meld into whatever you wipe it on with. Okay, it's so thin that if you pick it up, it tears. Because you don't want to put very much gold on if you can avoid it because gold's expensive. So gold leaf is incredibly thin. because all you want is to be able to see the outside of it. Doesn't matter how thick it is. Okay? But for him, he was looking at thinness, so he can get as few as possible. Okay? So he needed a way to detect it. So because it has a charge, anything that hits a charge, hits a fluorescent screen, it glows. In fact, is the only reason we could see the beam on the cathode ray tube, I don't know if you noticed it, but there was always a white background on behind it. That's because the beam was hitting a phosphorus. There was a phosphorus thing in there for you to see where it hit. Okay? Because the electron had a charge, charged things hit phosphorus, it glows. Okay? Fact is, that's how old TVs worked. Old TV, the official name for what you had was a CRT, a cathode ray tube. Okay, and all it did was shot a cathode ray, makes a beam of electrons, and to draw the picture, it just used magnets to aim that beam and go back and forth across the screen 60 times a second. So it just used the magnet to aim the beam and turn it on and off to hit little different fluorescent little dots on the screen that would glow when it hit. And if it hit a red dot, it glowed red. If it hit a yellow dot, it glowed yellow. Make sense? Actually, it wouldn't have been a yellow dot. It would have been just red, blue, and green are the primary colors. So it would just paint the picture like this. And that's why when you watch the old TV, if you watch a video of somebody watching an old TV, it's got that screen, it's got that black line that scrolls through. That's because at the time that video is taking, there's nothing showing up right here because the beam has gone to here, the glow has died up here, now it's jumping back up to the top without going through. So that's why I see a beam of darkness walking through, is because it's seeing that this was hit long ago, this is hit now, and too long ago it disappears. So now, now the diagram I'm going to show is every book I've ever seen has drawn the diagram that way, but it's not really what it looked like. Okay, but those are the pieces. You got a lead block, you got uranium, you got gold foil, and a fluorescent screen. You need the lead block to stop the alpha particles from going every direction. You drill a hole, the only way those alpha particles are given off in every direction, but the only ones that are going to come out are the ones that go straight out. So you got an alpha particle source that's aimed at gold foil and a way of detecting where it hits. Okay. So every diagram I've ever seen looks like this. But what it actually looked like, the actual piece of equipment, was this. Okay. Okay, so we'll see what's inside this circular thing, but the key is they had to take the air out because air is atoms. And you only wanted to hit the atoms in the gold foil. So the first thing they had to do is make an airtight and vacuum out all the air. So the testing devices over here, everything on this side of the table is a vacuum pump to get rid of the air. Okay? So all that is just get rid of the air inside there. And what was inside there is, you got the lead block. They drew in this hole. You can't see it. They actually had to draw it in because you can't see through lead. I don't have that good eyes. Okay? And they're going to put the foil right here. And instead of the screen going all the way around, it's just a little tiny screen, and it rotates. So yesterday you were looking at that little window and seeing the scintillations. Scintillations are where it glows, little green dots glowing. Well, that's what they looked at. Okay? Come on, do something. Okay, so they're drawing in the alpha particles. You can't see alpha particles. The only thing you could see would be, you'd be outside, and you'd see dots, and you'd count them. Okay? That's all you do. You'd see dots and count them. You put gold foil in the way. You look. You see dots, count them. And then here's how you changed it. Again, they're drawing in those alpha particles. You can't see them. And you just turn the whole top. And then you count again. So that's why it had, yesterday you could rotate it every 5 degrees and count how many hit. So that's what this was trying to show you yesterday. That when you fired the particles, wow, it fills up right away. Fire particles, fills up right away. But if I move it to, oh, gotta stop, turn it off. But I move it off to an angle, fire particles. There's particles, but it takes longer to fill up. Okay? So that's what he did, was he just recorded, well, I say he recorded, somebody recorded the how many hit at every angle around the atom. So can you see how this diagram represents those pieces? Okay. This is just that little window that goes all the way around. All the other pieces are there. So what did he expect? Well, he expected the alpha particles to go through without changing direction very much. He doesn't expect to see much change. Why does he have those expectations? Well, because he believed in Thomson's model of the atom. Okay, he thought Thomson's model was correct. And in Thomson's model, the positive stuff is all spread out. Thomson's model, the positive's all spread out, and you got little negative pieces stuck into it. Well, when that positive alpha particle comes towards that positive stuff, it's all spread out, and it can go right through it because it's not concentrated in any one area. Much like if I take a piece of paper, could I stop a bullet with a piece of paper? How about with a couple pieces of paper? Well, ask Teddy Roosevelt. Teddy Roosevelt was on a train, he was going to give a speech, put the speech in his pocket. He folded it up, put it in his pocket. Someone shot him. It hit the speech. And it slowed it down, slowed the bullet down enough that she didn't die. He finished his speech. Finished the speech, got back on the train, and they treated him. Didn't want to appear weak. Okay? So the paper stopped the bullet. How is that possible? Well, because the paper, like spread out piece of paper, it's all spread out, you run into one piece of paper. But if I take that same piece of paper and fold it, now you got twice as much paper. Fold it again, now you got 4 times as much paper. Fold it again, now you got 8 times as much paper. Suddenly you get layers. Will bullets go through a book? They get stopped, right? So you see that if I take the paper and concentrate it in an area, it stops things. But if it's spread out, it doesn't. And he thought the alpha particles had the positive stuff spread out. So right there. That's the wrong one. I had it here. I had it and disappeared. So when you looked at this one yesterday, and you looked at the plum pudding model, okay, the orange stuff is the positive stuff, and the dots are electrons. Okay, so this is, he thought the gold foil looked like. Okay, and he thought when you fired alpha particles, they could go right through like BBs can go through paper. But if I get it thick enough, the paper will stop the BBs. Make sense? Well, this is the paper all spread out. The positives all over there, so these positive pieces don't encounter very much positive. Okay? So they go straight through. So he expected to see just a bunch of dots on the screen back here. Okay? Because here on mine, the green's all the positive stuff, but it goes straight through. Now, because he thought the mass, the positive charge was all spread out, well, why is he doing this experiment? If he thinks it's going to go straight through, why is he doing this experiment? The answer is right here. Right here, when the alpha particle comes out at the end, it's got positive below it, but it doesn't have any positive above it. Everybody see that? That there's positive below, but not above. So that means this beam, and since likes repel, this beam is going to spread out a little bit. And that one's going to spread out a little bit. Because it's got positive on one side and no positive on the other. So it comes out the sides, it gets bent. Now I'm exaggerating here, but the smaller the atom, the sharper the curve. The sharper the curve, the more it'll get bent. So he decided that if he knew that if he could do the math, that if he could figure out how much it spread out, he could work backwards how big the atoms were that would spread it that much. Just like a more thicker lens bends light more. Okay? If I make it more, if I make it thicker and more concentrated, it spreads more. So, what he got? Well, first of all, he got what he expected. Almost all the dots were right there. Okay? But looking, he said there were some on the edges, so I don't think the first one spun. I don't think there was no reason for him to think it had to spin 180 degrees, but first one I don't think moved. We saw the end of the equipment, but the first version probably didn't move very much because he was only looking for a little spin. He didn't need it to go all the way around to see how much it spread, right? So he got once, but there were some on the edge, so he wanted to see where the edge really was. And when he moved it out further, there was still some alpha particles still bent that much. And he moved out further, and there were still alpha particles. And these right here, the ones that bounced off the gold foil, when he saw those, he knew his teacher was wrong. Because there's no way Thomson's model explained those ones bouncing backward. Okay, the quote they always give tries to give a sense of scale. Okay, he says, I would not have been any more surprised, when you saw those ones that came back, I would not have been any more surprised if I'd fired a 15-inch cannon at a piece of tissue paper and the shell had bounced off. It sounds like he's exaggerating, but no, he did the math. The alpha particle to the Thomson's model should be like a cannon shot at a piece of tissue paper. It should tear right through without even being affected very much. He did the math that said it should be that thing. So he's got to explain why most went through and why a few bounced back. That's what he's got to explain. So first, why did most go through? He came up with the easiest explanation. The atom is mostly empty. Why did most of them go straight through? Because they didn't hit anything. That's a pretty easy explanation. Why did they go straight? They didn't hit anything. Okay, now, scientists sometimes under-exaggerate. When they say mostly empty, okay, a baseball, this is the analogy in your reading. A baseball field with nothing in it is empty. A A baseball field with a marble at second base is mostly empty. And that's the scale. A marble in a baseball field. Okay. That's kind of tiny. Okay. Now, it had to have a small center because it was mostly empty. And that center had to be dense enough that the alpha particles wouldn't push it around. It had to be small and heavy. Small and heavy makes dense. And the alpha particles are deflected if they get close enough, because positives repel. That positive alpha comes up, if it comes up with a positive charge, it's going to be pushed one direction or the other, which will change its path. See, that's just it. He knew how hard it was to change an alpha particle's path. He'd already measured how hard it was to change the path, so that's why he knew it was like firing a cannon at a piece of tissue paper. You know how much energy they were traveling with. So this is me trying to draw it. The closer they get, the more they bend. Right? So on a larger scale, what you guys saw yesterday, when you did the Rutherford atom and you fired alpha particles at gold foil. Turn on traces so we can see them. There we go. Huh. Doesn't seem to be running. Let's see. Can I see it on this screen? Oh, the traces are purple. It's really, really faint. But notice where they turn. Well, maybe we can see it better if we zoom in on the atom, on that dense positive piece. So this is protons and neutrons, positive and neutral pieces, so it's positive. Okay? The ones out here aren't affected very much. As they get closer, they get bent more, and if they come right up the middle, they can bounce back. So by the number that bounced back, he could tell how big the nucleus was. Because the bigger it is, the more we bounce back. Okay. Does that make sense? So it explained his observations. Why did most of them go through? Because the atom is mostly empty. Okay. Why did a very few bounce back? Because when they got close to that positive nucleus, they got pushed off to one side or the other. Okay. Now, we're talking about in terms of idea. He did the math behind how hard H1 was pushed. So it wasn't just, oh, I think this is what happens. But it took him a long time to come up with it. Okay? And that's the kind of things you get, prizes for, like Nobel Prizes. Okay? So since most of the particles went through, it was empty. Mostly empty. And what there was because the positive pieces turned so much, the positive piece in the atom had to be really heavy. So you got a really small region that's really heavy, a big mass over a small volume. That gets you a big density. And that small, dense, positive area is known as the nucleus. So now the nucleus of an atom is not the same as the nucleus of a cell. Okay? I had some people saying the nucleus of the atom controls the atom. No, no, it doesn't control it. It just determines what kind it is. Okay? There's nothing coming out of it. No RNA coming out so that it can be transcribed. There's nothing going into it. Okay? It just sits there. And we'll talk about it changing. We'll talk about the nucleus along the way, because it can change. It's just hard to do. So, now, the other pieces, okay, actually were found much after Rutherford. First, they figured out that what made it the type of atom was how many electrons you could knock it off. Okay? But then they found out that that nucleus was made of two pieces. A proton, and a protons, I put 1840, sometimes to say about 2,000 times heavier than the electron. And the neutron, okay, the neutron doesn't have a charge, but it's got the same mass as a proton. Well, not quite exactly the same mass. If you look, I'm not sure where your book stops, but for the first three sig figs, they're the same. In the fourth sig fig, they're different. But for all intents and purposes, they weigh the same. Yeah, it's just a tiny difference, yeah. Okay. Your book doesn't tell you how they know about neutrons, because neutrons are going to be a pain. Think about what they've done so far to find the pieces. They use charges. Thomson used charge to move a positive and negative thing. Rutherford used the positive charge to get it to affect that positive in the nucleus. How are you going to find something without a charge? How are you going to grow something without a charge? How are you going to get something without a charge? Well, the answer is, nope, that's not it. That's not easy either. Oh, there it is. Okay, so what they do is called mass spectrometry, mass spectrum, okay? And they take a sample of a pure element. They took a sample of a pure element, and outside of the machine, they knocked all its electrons off. Okay? Talked about X-rays being able to do it. You couldn't control how many. Well, they put in enough X-rays, they made sure it knocked all the electrons off, whatever you had. And they shoot it into a slit so that you can make sure they're all together. And then they passed it by a magnet. Now the magnet, we talked about magnets and charges being at right angles. So Thomson could bend his beam with a magnet. They're bending this beam with a really strong magnet. Okay? And when they bend the beam, the heavier ones are harder to turn than the light ones. So when they come out separate from each other. I've separated the blue, the green, and the red from each other because the red doesn't bend as much because it's heavier. So what you end up getting is a graph of how many things weighed that much. So all you end up with is a simple little graph. It looks like this. Okay, this is the 69. So this is gallium, and with gallium you got two lines. Okay, and those two lines, they knew how much weight separated them. You could tell how much weight separated them, and the separation was about the weight of a proton. But they were both gallium, so they had to have the same number of positive pieces. Because that's what made them gallium. They didn't know they were protons, but they knew how positive they were. That you could line up the elements by how positive you could make them. Hydrogen, you can make a 1 positive. Helium, you can make a 2 positive. Lithium, you can make a 3 positive. Yeah. So they knew they were all both gallium, but they had different weights. This proved Dalton was wrong. He said atoms of the same element are identical. Apparently, there are 2 kinds of gallium. One that's heavier than the other, and there's more of the light one than the heavy one. Different elements, different spectrum. So this is sulfur. Almost all of it is here, but there are a few little tiny peaks along the way. Just a little bit of other stuff. Cadmium has got 7 different. Okay, and those are isotopes. Okay, so they're separated by whole number jumps. Tells you had to add whole number pieces. So this one they did by mass again. Okay, which is what Dalton used. Dalton used mass to figure out whole number pieces, right? Well, this shows us whole number pieces too. There's an individual step between each one of those on cadmium. Okay, so the only way I could get that kind of graph is if I added whole pieces, whole neutral pieces, the neutron. Okay, so that's how they knew they were neutrons. I thought you should know how they know they're neutrons, because they're the hard ones to find. Okay, but what is our view of the atom? The atom is mostly empty. You are mostly empty. The wall is mostly empty. How come you can't walk through the wall? Because emptiness should be able to walk through emptiness, but you can't. Why is that? Okay, we got 2 regions. We discuss when we talk about the atom. 2 regions are the nucleus, that's where you're going to find the protons and the neutrons. All the heavy pieces are in the smallest part. That's why that smallest part is really dense. If you put all the heavy pieces in the smallest part, it's going to be dense. Okay. And then electron cloud. Electron cloud we're going to define as a region where you might find the electrons. Where you have a chance of finding the electrons. An electron cloud is not a cloud of electrons. That would be a bunch of electrons. Here's my evidence that electron cloud is not a cloud of electrons. Hydrogen has an electron cloud. Hydrogen only has 1 electron. How can 1 electron be a cloud? Well, it's a cloud of probability. It's a cloud of where you have a chance of finding the electron.
If that cloud is a probability, is it the same for every atom?
Nope.
Or more atoms?
Different atoms have, and that's the next unit. So we're going to do the nuclear stuff, and then the next unit is going to focus on those electrons and see how they are structured. Because how they're structured leads to properties, which is what none of our models have explained any chemistry yet. I don't know if you noticed that. The only thing they've explained is laws of multiple definite proportions. They haven't explained why anything else happens. We don't have a good enough model because our model of the atom, according to this, and this is where we're stopping this unit, our model of the atom doesn't include anything that tells us why one chemical reacts and another chemical doesn't react. And they knew that about their model of the atom, so they knew they had a lot more to learn. Yeah. Okay, so electron cloud. Okay, so your book described it carefully, a cloud of negative charge. All the negative charge is distributed all the way through that cloud. I drew it as a sphere. It's not always a sphere. Okay? So, but that's where the electrons are. So the thing that makes up most of the atom weighs the least. Okay? Because here's the relationship. between an electron and a proton. If the proton was a mass of a car, an electron would be a water bottle in the front seat. That's 2,000 times heavier. Okay? So when we say the lightest piece is taking up most of the space, it's really the lightest piece by a lot. And that's one of the things is electrons are light, so they're easy to move around. The reason why Thomson couldn't separate the positive parts was because they were all together in one big unit, and big units are hard to move. That's why he never found any positive pieces. Because eventually somebody drilled holes in Thomson's cathode ray tube on the anode, and if they put hydrogen in, they could see rays going the opposite direction, going away from the positive charge. Only because hydrogen is the lightest nucleus. So you get the hydrogen nucleus to go backwards. Okay. All right, so this is something you've learned like every time you ever study the atoms, so I'm going to go kind of quick. Okay. Okay, we got 3 subatomic particles that we have to worry about. We're not going to go to there's like 400 of them. We're only going to study maybe 4. Might throw the quark in there. Okay. So electron, its symbol, lowercase e with a negative sign. When scientists are too lazy to write electron, they wrote lowercase e with a negative sign. Its charge, negative. Okay, oh, sorry. The proton is a capital P with a plus sign. Oh, no, not lowercase p with a plus sign. Lowercase p with a plus sign. What do you think the symbol for neutron is? N. And how do you say it doesn't have a charge? You put a 0. So that they know you didn't forget it. I didn't forget that this had no charge. That, you don't mistake it just for the letter N. Charge, just what they say on top. Charge comes in units though. It comes in pieces until you get smaller than the atom. It gets smaller than these pieces. But as protons, electrons, they have full units of charge. It's either fully positive 1, fully negative 1. They're integers, unlimited sig figs, if you have to multiply by them. And the neutron, 0. Okay, relative mass. Relative means compared to each other. Okay. So if the proton weighed 1, then the electron would weigh 1/1840th. If the proton weighed 1, then the electron would weigh 1/1840th or 1/2000th of that. Okay, how much would the neutron weigh? So as far as we get, it's about 1. And if you look at the actual mass, you got 9.11 times 10 to the negative 28th grams for the electron. We've seen that one a couple times. This is the one that Millikan found. Once he found the unit of charge, he could figure out the mass of the electron. Okay. Now, protons 1.67 times 10 to the minus 24th. See, minus 28 to minus 24th. That's 4 zeros, guys. Okay. And this one, and if you go one more sig fig, the proton and neutron are different. So people tend to stop at 3 sig figs. But one more sig fig, they're slightly different. Okay. So it brings me to my favorite joke of the year. There were 3 subatomic particles walking into a bar. The proton went to the bartender and says, "I'll have a root beer." The bartender says, "Are you sure?" The proton says, "I'm positive." Okay, the neutron says, "I'll have a root beer too." Bartender says to him, for you, no charge. The electron says, hey, I've been coming here for years. You have never given me, what do I got to do to get a free root beer? Well, bartender, hey, quit being so negative. Everybody knows you're a lightweight. He's a lightweight. So, see, the three subatomic colors, that's the important part. Positive, negative, neutral, and the electron's a lightweight. My favorite joke of the year. Okay, so it says experiment review. Guess what it's going to do?